Hello everyone, this is the second video of the dimension reduction module. In the first video, we talked about data redundancy analysis, and basically we were able to sort of examine the relationship between different attributes and see how much similar information those attributes are carrying. And based on the level of similarity, we might have to make a decision to remove or integrate some of those attributes. First video was taking a parametric approach towards dimension reduction. When I say parametric approach, I mean that the intuitiveness and the meaning of the attributes are still very important for the purpose of the analysis. In this video, we are going to take a non-parametric approach for dimension reduction. We're going to be learning about principal component analysis, or known as PCA, which basically acts as a method to gather up all the information in the least number of possible attributes. PCA is great in a way that it's non-parametric, so you don't have to worry about examining the relationship between attributes. It basically does the whole job for you, and you will end up having 3-4 attributes instead of like so many, with the most possible variance in them or information in them. But also you will going to lose that intuitiveness of the attribute. That's a trade-off that you have to figure out if you're willing to accept. Before we get to the video, I'm going to mention the fact that PCA is a very well-established method, and it has a lot of theoretical background. While they are important, but you have to pay attention that it's not going to be the main focus of this video. The main focus of this video is just going to feature an example of using PCA to do data reduction, and we are not going to be going over all the theory behind PCA, but what we are going to learn is how best we could be using PCA for the dimension reduction. So as usual, we import the modules, and then in this video, we are going to be working with another module. sklearn has a lot of statistical methods and functions that are very useful. In this video, we're going to be using PCA. So I'm going to import that. And also, we are going to be working with another data set in this video. We are going to be working with serial data set. This is basically a list of different serials, 77 different serials, and they are described by 16 attributes, which one of them is name and 2 of them are categorical. So there are 13 numerical attributes here that are describing the different cereals, such as the level of fat, sodium, fiber, and so on and so forth. The attributes here are very intuitive, and you can just look at the attribute name and you will have a pretty good idea what they are about. So let's just get to it. Before we see a full-blown PCA, let me show you a small version of it. So I'm going to reduce my data set into only calories and rating. So now I have a 2-dimensional data set. It's only calories and rating. Now I'm going to apply PCA on a 2-dimensional data set. So you want to pay attention here. Normally, you would never apply PCA for a 2-dimensional data set because the dimension is very simple. We could be looking at a scatter plot and we'll see only relationship between the attributes. So PCA is not going to really be beneficial for a 2-dimensional attribute data, but we are doing it for the purpose of learning how PCA works. So it's a scaled down problem just to learn about PCA, and then we'll look at the full-blown one. So all you need to do to use the module, you'll be say PCA1, and I want the number of components to be 2. So you could pass the number of components, or you could just leave it as blank. So since I want 2 number of components here, I have specified 2 number of components. So I say this is my PCA, and then I say fit, and I'm fitting to the the selected dimensions, only those 2 dimensions. So this data set. So once I run this, now my PCA is performed and everything looks good. Now when I want to see the result of the PCA, is basically has transformed my data to create 2 new dimensions instead of the 2 dimensions I had, with 2 purpose, with 2 goals. So these are the 2 new dimensions, and this is the scatter plots for the original data rating, and this is the scatter plot for PC1 and PC2. If you look at these 2 attributes, these 2 charts, you could see these 2 goals are being met on the transformed data. The first PCs explain most of variation. So when it comes to data mining and pattern recognition, when we say information, what we really mean is variation across the population of data objects for one attribute. If the variations of 2 different attributes are very similar, they have high correlation. And basically what PCA does is says, I want to transform the data in a way that the first PC explained the most possible attribute. So here, if the PCA were to put the axis, or transform the data by drawing a line in here, that line would be describing much more variation than the X and Y dimension, the calories and ratings here. So that's what it does. It sort of accepts the first dimension to go through the part that has the potential to describe most of the variation. And as you can see, that's the first PCA. If you look at the data, basically this is this point, and these are those 2 points. So you can see that this is that line that goes through the PCA. So the first goal is that. The second goal is all of the PCAs, all of the PCs, principal components, are orthogonal, meaning that they have 0 correlation with one another. So once I figured out my dimension here, I choose the second dimension in a way that it's going to be orthogonal to the first dimension, and that's going to be PC2. So let's look at the some other things about PCA. One of the things that you want to pay attention here is the fact that PCA is not going to change the variance, the total variance in your data. So the total variance in my data is 576.95. This is the total variance that exists in the data. But the thing is, some of these variants are shared, and by re-representing the data, it can push the shared variance to the first few PCs. So now, if I look at the PC's variation, I can see now, instead of having 379 portion of the variance for the first attribute, I have 498. So most of the variation now is pushed to PC1. But you can see that the total variation still is completely the same. So it's not going to add or decrease any variation. It re-represents the data in a way that these 2 goals are met. The first PCs explain most of the variation, and all of the PCs are orthogonal. So now that we were able to look at PCA from in a simple example, simple data set, let's do the PCA on all of our data. But we are going to apply to all of the numerical data. So I am making sure that I'm only getting the numerical data. So I'm not getting these 3 attributes. That's why what we have here. So I'm getting all of the data, and everywhere that I have a missing value, I'm also dropping it. Once I run this, now I can see that the total variation in my data is 13,000. But once I pay attention, I can see most of the variation now is explained by the first PCs. 53%, 54% of the variation explained by the first PC. And then after that, I have 5,000, which is around 38% of the variation. Together, they now explain 92% of the variation in the data. So pay attention. We had 13 attributes, and now with PCA, I'm able to explain 92% of the variation in the data by only 2 dimensions instead of 13 dimensions. That's a pretty good deal for concising your data in a way that you have it much more manageable. But it comes at the cost of now PC1 and PC2 are sort of just information holder. They don't have any intuitive value, and you cannot be able to use these attributes as a way to apply algorithms and get intuitive results. You might be able to run predictive algorithms and predict the future and everything might work, but it's not going to be intuitive. You're not going to ever know why those predictions work in the way they are because you chose to go with non-parametric dimension reduction. Another thing we want to pay attention here is, as you can see, I didn't do standardization or normalization of the data. Let's normalize the data first and then see if it's going to change anything. Once we do normalize the data, we will see that some of the variation, it's not as successful as before, basically. So the first PC only explained 30%, and it's not until the PC6 that you have 90% of the data. So you want to pay attention to the fact that normalization does matter for PCA because the scale of the data is going to change the amount of variance that they have. It's not working with the standard deviation, it's working with the variance. The higher scale, the larger variance. But in experience, most of the time where the PCA for the original data and PCA for the variance for the normalized data are different, the reason is basically, for the most part, because there are some outliers in the data. And those are the reason that these are changed. So if you have not taken your time to figure out those outliers and analyze the data for that purpose, it's better to use normalized data for PCA. So let's go with this PCA. So now we can have 90% of the information in the data by only 6 PCs as opposed to 13 PCs and 100% of the data. So let's just go with them. So now that we have done the PCs, let's go ahead and do some visualizations just for fun. So this visualization is showing you the PC1 and PC2. And as you can imagine, this should be having 0 correlation. As we see, it does have 0 correlation. So you can see that there's no relationship between PC1 and PC2. They're supposed to be orthogonal, and they are orthogonal. But now we can remember these points each represent a serial, and this figure is showing 52% of all the information in the data. So by just eyeballing, you could be seeing some similarity between your attributes. You could be doing some clustering with visually clustering. So you have a cluster here, 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 and you have a cluster over there. And this is extremely useful as far as being able to look at the data, most of the information in the data, by just this. So this is an extremely useful visualization. It doesn't have intuitive understanding of what attributes have led to this, but it does have a good comparison points between the data objects. Now you can be able to see what attributes are more similar to one another just visually. So now we know that there are, around 1 here, 2, 3, 4, 5, 6 clusters in the data by looking at 52% of the information in the data. We saw that we could be adding more dimension to scatter plot. So let's apply it here. Using color, I'm also adding PC3. And now I can see 67% of the information in this data. Pay attention here. When you're looking at this visual, you want to pay attention to the fact that PC1 and PC2 are taking precedence over PC3. So even though you see colors, that this color is similar to that color, the fact that this is further apart should be more important. And we come back to our old restriction, like we're human, we see things the way we see things. So as useful as this is, but you know, we're still have our limitations. So we could be also adding another level by size and PC4 as a size. But again, as you look at this visual, you can see this visual is becoming more overwhelming than intuitive and helpful as far as being able to see if there are patterns here. I think if we paid attention to what we are looking at and stay vigilant, at the 3 dimension we still could follow and see possible patterns, and this could be really useful. But once we get to 4 dimension, it becomes overwhelming. It is true that this visual is showing around 80% of the information in data, but it's no better than looking at some numbers because it's not adding any intuitiveness by adding dimensions because I'm overwhelmed. So there is like a trade-off. You want to pay attention how much visualization can be helpful for you as far as being able to add more dimensions to the visuals.